So the last thing we're going to look at here is the molecular geometry, basically shapes of these different molecules. So you might have noticed a second ago that we had this acronym too, VSEPR. Well, that stands for Valence Shell Electron Pair Repulsion Theory. Isn't that a mouthful? That's why they abbreviate it, and I don't think the abbreviation is too much better, but that's my opinion. So anyway, this is just a theory for being able to predict the geometry or shape, basically, of the different molecules we're looking at. And it's based off the number of electron pairs surrounding a central atom. So most of the time you have one atom that is dominant and then other things that pair with it. So you have bonding things and things that are just electrons that are already paired together moving around it. But electrons push away from each other. So there's a repulsion, right? Like charges repel. So that means that you're going to end up with them pushing away in order to create a certain shape. A good way to think about it is if you have helium balloons or a balloon that's actually being pulled up in the air. If I have one balloon on a string, then it's pretty easy for that one balloon, here I'll draw it, to be seen, right? But as soon as you add a second balloon, they're going to start bumping against each other and try to rearrange their shape till they can get nice and calm again, right? And you're going to end up with something that's slightly different from all of that, because then they have to rotate around, and so you're going to get one that's more over here and one that's over here, and then two strings that move down kind of in a V shape, right? If you add another balloon, that's going to create even more chaos, and they're going to have to find a way to orient. And normally they wouldn't even stay like that, right? They end up finding a better way where you end up with all of them paired together in a three-dimensional type form. So you get 1, 2, 3 somehow, and they're all still going together, correct? Well, electrons do very much the same type thing. It's based off, though, how many are bonding and how many are just lone pair. Remember, lone pair isn't bonded. It's just what's already there, and we consider it an electron pair. So things like, let's say, nitrogen. All right? Nitrogen has two that are already bonded. That's a lone pair. And then it has one loose that it can bond with things over on each side. So our lone pair is just these that are already bonded together. When the others bond with something, they're going to create a bonding pair. And that's the difference between those two. You can figure this out by doing just what I started to do. You draw the Lewis dot diagram, okay? So let's say we're looking at nitrogen and chlorine, okay? Again, nitrogen has two that are already bonded together and three open. It has 5 electrons in that valence shell, right? Chlorine has many more, but it's going to have to move around in order to bond with nitrogen, right? Now it has plenty of pairs here, because it has to have 8 total. But what we're really concerned about are these right here, right? So you can see that it has 3 bonded pair and 1 lone pair. Well, thanks to a chart like this, we can start to figure out how it's going to look based on the number of bonds it has that are bonded pairs and lone pairs. If you take a better look at this, things that don't have any lone pairs, they separate to the maximum amount in a 360 type fashion, okay? So as soon as you have 2 bonds, it's going to be linear because they're going to move opposite sides as far apart. Notice 180 plus 180 is 360, maximum distance. And it wouldn't matter at what 3-dimensional angle you move that, it's always going to be on opposite sides. It turns out if you don't have any lone pairs and you have 3 bonds, it'll still follow that 360 rule. That's the maximum they can get away from each other and still have a full distance around. So that would stay pretty much linear or two-dimensional there, even in a three-dimensional world. But by the time they get 4, well, it's easier for them to move in 3 dimensions, and notice this doesn't add up. If you do 4 times 109.5, you're not going to get 360. That's because they're now moving in 3 dimensions. But you can trust us, between the bonded pairs, that's what this angle is, by the way, you're going to get 109.5 degrees is the maximum they can get away from each other. Think about it like in-laws that don't like each other at a family reunion. You'll find them at as far away places as you can at wherever you're meeting. However, when we introduce a lone pair, lone pairs are already more electrons or more electronegative, more repulsive than those just that are bonded pairs. And so that's going to push these down further, and so you get a smaller angle between the bonded pairs, and it would be a bigger angle between the lone pair and the bonded pairs. If you get 2 of those, well, you're going to get even more until you get these different shapes. There is a notation for this called the axe notation. It's a little confusing because you just use an A will represent your first central atom. So we're looking at only one atom, the one in the middle, right? The X, that's going to be the number or represents bonded pairs. And to know how many we're going to do, that's why it has a subscript of Y. That's the number of those bonded pairs. E represents unbonded or our lone pairs. And the subscript is Z, so that would represent the number of those lone pairs. So something like this, chlorine and hydrogen, well, chlorine's our central one. You're going to have, with it, that's our element. And then for our bonded pairs, we have 4, and it doesn't have any that are lone pairs. Or water over here, that's going to be a little bit different. Oxygen is actually our main one, okay? So with it, you're going to have 1 oxygen molecule. Notice the 1 is usually our main one, and it's going to bond twice, so it has 2 bonded pairs, but it also has 2 lone pairs. The rest is just to give you a basic idea of what these look like, and the shape is called something fun. So this, a triangular pair. This one is a tetrahedral shape. Notice that these are still all bonded, so it's equal distance away from all the parts. This one is called bent because this is the first lone pair that we have. So technically this angle is a little bit smaller than this one, but not by a lot. That's why it just says slightly less than 120. Notice if these were all 3, just our bonded pairs, it would be exactly 120. This is a trigonal pyramidal, and so notice we neither have a lone pair, so all 3 of these are pushed together a little bit closer than the angles between the lone pair and the bonded pair, and so there would be 107 between these bonded pairs. And then we have another bent shape, because it doesn't have a very good name for it, but we have 2 lone pairs. They would be in equal distance from one another, but there's a greater distance between them and our bonded pairs, and our bonded pairs only have 104.5 degrees between them. And that's pretty much all of them. Just got to take a look.